All right, today we're diving into one of the biggest, most ambitious challenges in all of science. It's a question that smashes together biology, computer science, and honestly, a little bit of philosophy.
It seems like such a simple question, doesn't it? But the answer is, well, it's unbelievably complex. To even think about simulating a brain, you first need a perfect blueprint. And then you've got to have a way to test if your simulation actually, you know, acts like the real thing. So let's see how scientists are tackling both of these massive problems. So here's the game plan. First, we'll dig into the incredible, painstaking effort to map the brain's wiring. Then we'll see if we can use those maps to actually predict what the brain does. We'll check the report card. How well are we doing right now? And finally, we'll look ahead. What's next on this absolutely monumental quest?
Okay, part one, the blueprint, or connectomics. Every big construction project, right? It needs a blueprint. For the brain, that special blueprint is called a connectome. It's the full map of all its crazy, intricate wiring.
Think of a connectome as the ultimate circuit diagram. It's a map that doesn't just show you every single neuron, but, and this is the important part, every single connection, every synapse between them. This is the physical hardware that makes all our thoughts and actions possible. And making one of these maps, wow, it is a truly mind-boggling task. First, they take brain tissue and slice it into thousands of layers, each one thinner than a human hair. They image every single slice with an electron microscope. Then, powerful computers stitch all those flat images back together into a 3D model. And after all that, human proofreaders have to spend literally tens of thousands of hours just correcting the mistakes the computers made. It's a huge effort. All of that incredible work led to a massive breakthrough you see here, the HemiBrain project. This is a nearly complete wiring diagram for a big chunk of a fruit fly's brain. It's a huge landmark, our first really detailed blueprint of a brain this complex.
And the scale is just staggering. We're talking about almost 25,000 neurons and 20 million connections between them, all mapped out. This gives us a look we've never had before into the circuits that control everything a fly does, from flying to finding food.
But let's be real. A fruit fly brain, as cool as it is, isn't a human brain. So what happens when you try to use these same techniques on a piece of our own noggin?
Well, this is what happens. This is the H01 dataset. It is a map of just 1 cubic millimeter of the human brain. That's a tiny sample, smaller than the head of a pin, that was taken from the cortex of a patient during a surgery. And here is where things get absolutely wild. This tiny, tiny piece of human tissue has an estimated 150 million synapses. That is more than 7 times the number of connections in the entire fruit fly hemibrain we just saw. The data for just this 1 cubic millimeter takes up 1.4 petabytes. That's like a million gigabytes. It's just an insane amount of information. So we're getting these blueprints, these amazingly detailed static maps. But a map of all the streets in a city doesn't tell you anything about the flow of traffic, right? To get how the brain works, you have to see it in motion. Which brings us to part 2, the test. This is where we try to go from that static map to a living, breathing, dynamic simulation. And the ultimate test of that is prediction.
Yeah, this really puts the challenge into perspective. If the connectome is the brain's hardware, the physical wiring, then a good simulation has to predict the software. It has to predict the actual patterns of electricity, the neural firings that flash across that hardware from one moment to the next.
So for this test, scientists needed another perfect subject. And they found it in the larval zebrafish. Because these little guys are transparent, we can actually use powerful microscopes to watch and record the activity of pretty much every single one of its 70,000 or so neurons, all at the same time, while the fish is alive and kicking. It's the only vertebrate animal where we can do this right now. This incredible ability led to something called the ZapBench Challenge. You can think of it like a weather forecasting problem, but for the brain. The researchers take a few seconds of real, recorded brain activity, feed it into a computer model, and then the model's job is to predict what all 70,000 of those neurons are going to do for the next 30 seconds. Part 3, the verdict. So, this is the moment of truth. How did the models do? Can our current tech actually predict what a living brain is going to do next? And this is so critical because, as the creators of ZapBench themselves put it, prediction isn't just a cool trick. It's a fundamental test. If you can't predict what a system is going to do, you can't really claim that you understand. And here you can see the results for yourself. On the left, that's the ground truth, the real, beautiful, shimmering patterns of activity that were actually recorded from the fish. On the right,
That's the prediction from one of the best computer models. And you can see it gets the general vibe, right? The right areas are lighting up, but those fine grains, specific little flickers of light, they're just not quite the same.
This chart really nails it down. If you just make a naive guess, like assuming nothing changes, your accuracy is way down here. The machine learning models are much, much better, no question. But they are still a very, very long way from a perfect prediction up here.
So the takeaway is pretty clear. Our ability to predict what an entire brain is doing is promising. It's definitely better than just guessing, but we are nowhere near a perfect simulation. We're capturing something real, but there's still a massive gap.
Which brings us to our last section, the future of simulation. So what's holding us back? What are the next big hurdles on this epic scientific quest?
Well, the list of challenges is pretty long. For starters, our data itself isn't perfect. Those connectome blueprints still have tiny errors. And our imaging, while amazing, is still too slow to capture the true millisecond speed of neurons. But then there's a whole bunch of biology we're just beginning to understand. Things like glial cells, which, by the way, actually outnumber neurons in the human brain, or other ways neurons talk to each other. Our models just don't account for that stuff yet.
Look, what we're seeing from projects like the HemaBrain, HO1, and ZapBench is absolutely groundbreaking science. We have our first real blueprints and our first true predictive tests. But it's so important to see these for what they are. They aren't the end of the journey. They're the very, very first steps. The starting gun has just fired. And all of this leaves us with one final, really deep question. Let's just say decades from now, we solve all of these problems if we finally build a model that can predict every single neuron's firing perfectly. Have we actually simulated a mind? Or have we just built the world's most complicated puppet? That's the question that sits right at the heart of this entire quest. Thanks for joining me.